Now it's my pleasure to introduce the last invited speaker of this workshop, Professor Doina Brickup at McGill University. She's also heading the new DeepMind lab at Montreal, and before that she got her PhD at the University of Massachusetts, and she has been doing some very groundbreaking work related to hierarchical reinforcement learning, in particular in the framework that I think is one of the most used in hierarchical reinforcement learning now, which is the options framework. And we're very excited to have her in this workshop today. So please welcome Doina Brickup. Thanks.
So much of what I will talk about today is joint work with my PhD students Pierre-Luc Baton and Jean-Arc. Jean is somewhere in the room probably. So I was going to start this talk, as I usually start these talks, by telling you about how awesome options are. And given the amount of papers that we're looking at the options framework today, I decided that was not necessary. And so instead I'm going to sort of take you on a trip down memory lane. This is a 1998 webpage of workshops at NIPS. You probably can't really quite read it very well. There were 2 days of workshops, just like now, beginning of December. There were 12 workshops on each day. We had a workshop back then on hierarchical reinforcement learning, which I co-organized with Ron Parr, the author of the hierarchical abstract machines framework, and Tom Dietrich, the author of MaxQ, and Leslie Kelvin, who had been thinking about sort of temporal abstraction and controllers in robotics and so on. So that was a very exciting workshop. We had about 60 people. This was back in the days when NIPS always had the workshop somewhere with good skiing. Obviously, we don't fit on ski slopes anymore. It's also kind of interesting to see some of the commonalities and differences between the topics of these workshops. So, for example, back then, SVMs were all the rage, so there was like a lot of large margin classification. But there are actually some topics that are really quite common then and now, like sort of straddling neural representations and concepts, for example, and of course, this topic of hierarchy and abstraction in reinforcement learning. So I will be telling you about work that we've been doing for option construction. Options, this is just a notational slide, have an initiation set, an internal policy, and a termination condition. So you think of this in terms of embodying some kind of a controller. I wanted to point out a connection which I think perhaps fewer people talk about or think about, which is this connection to sort of pure programming. So you can think of an option essentially as a behavioral program that executes typically in call and return fashion. So you have a little subroutine. It has certain conditions when it can be called. If it's called, it's pushed onto an execution stack, and then you sort of go on and choose primitive actions according to the subroutine. That's the internal program, and then at some point, this terminates and sort of pops back up the stack and something else is called. And so once you start thinking in that framework, you realize that there's many things you could do. For example, you could have local variables inside of one of these subroutines to count steps or to look at cumulations of features or other things like this. So this is an extension that you can look at. Also, of course, functions can call each other on multiple layers. So even though a lot of the work that we see is actually 2-layer primitives and then options on top, in principle, you can build hierarchies that are much deeper. But call and return execution is not the only thing that you can do. Another model that people have looked at a lot is what's called interruption. So that means if an option is executing, something else that's better can come in and sort of cut it off. That's a specific form of concurrency. I think there's actually a lot more potential in other models of concurrency to be explored with ideas like options. And the other thing that I want to point out, and this relates a little bit to Matt's talk earlier, is that there is a memory, in some sense, that's encoded in the sub-goal of an option and what an option is trying to do. And that has to do with the agent's current goal. What is it trying to achieve? So oftentimes we think of state as a summary of the past, where has the agent been. The identity of the option is telling the agent what is it trying to achieve. So options have been around for a long time. For a long time, we've known how to learn options in the presence of given subgoals, for example. the frontier really is option discovery, and so in the last few years, there's been actually a lot of work in terms of trying to figure out what's a good set of options or a good set of sub-goals. It's a representation discovery problem, and Matt's nice talk pointed out some ways in which we could do this. I'm going to talk about a specific line of work that we've been pursuing with the motivation of achieving sort of continual lifelong learning in our reinforcement learning agent. And so for a long time, people have looked at specifying sub-goals, and a lot of the methods that exist, while very nice, they're very combinatorial in flavor. You have to tell the agent where to go, and the set of options has a certain value, and so on. We decided to look at ways of doing this if we have just an optimization objective, and we try to solve this optimization objective in a gradient-based fashion. And we were really intent on having a model that supports both discrete and continuous states and actions, where the agent sort of learns over time, and we don't have to specify a lot at the beginning. And also, one of my pet peeves has been that it's always been hard for these methods to work well within a single task. Often the motivation for having options has been stated as having a transfer learning framework. And instead, we really wanted to see if it's possible for an agent to learn temporal abstractions and solve a problem at the same time, and solve the problem faster than it would otherwise. And so in order to solve these issues, we looked at the inspiration at the classical reinforcement learning model called the actor-critic architecture. So in actor-critic, you have the policy, which is the actor, and you have the critic, the value function. And essentially, the value function is telling the policy which direction it should go in order to improve its rewards. And it's an interesting framework because it has a very clear optimization objective. You just want to get as much reward as possible. It's the natural reinforcement learning thing to do. It's continual learning. You keep getting states and actions. You keep getting these gradients. The policy improves over time incrementally. And it can handle discrete and continuous states and actions through various forms. And so we devised a system that is very much like actor-critic, but which we call now option-critic. So the main distinction is that instead of just having one actor, one policy that's choosing primitive actions, now we have many actors, okay? And so these are the different options. They're in the sort of little boxes on top. They each have internal policies and termination conditions. We're going to ignore the initiation sets for now because they're a bother and I'd like to get rid of them anyways. And so you have on top a policy that chooses among these options. At the same time, the structure of the critic is just a slightly bit different because we have to keep track of a little bit of extra information, and I'll sort of spell that out in a minute. So the idea is that we're going to parameterize the policies, the termination conditions of the options, the policy over options, and now we're going to use the critic in order to provide gradients for all of these quantities at the same time from the single stream of experience that agent is seeing. And so the formulation that we're going to be working with is there's one parameter vector theta, okay, that has the parameters for everything. We have one objective, which is to optimize return. And this is the usual sort of policy gradient kind of objective. And in order to kind of work with this objective and optimize it in this framework, it turns out that it's useful to think of an augmented MDP, okay? In a real MDP, you have a state and an action. In an augmented MDP, instead of just having the state information, you have the information of the state plus the identity of the option. Okay, so think of this as the state plus the goal that you're actually trying to achieve described in some form. And so now you can work with this gadget, and you can write down your objective and take derivatives, and you end up with something like this. So we have a paper at AAAI last year that describes this framework. This is a little bit of a generalization of the math in that paper, and it's kind of interesting. So the gradient ends up having 3 terms, okay? The first term is telling each option how it should improve its internal policy. And the basic idea is you should take primitive actions that are better. Okay, so that's very intuitive. So each of the options is individually trying to take more frequently the primitive actions that are looking more promising. The second term is the one that twiddles the termination conditions. And so the gradient that's coming in the termination depends actually on the advantage function. The advantage function turns out to be a really important construct that tells you how much better a given choice is compared to the average choice. And so in this case, we want to know how much better is the current option compared to stopping it and then switching to whatever the policy over options would do. And the idea is if the current option is better than average, then you should actually keep doing it. And so the termination condition is going to be pushed to lengthen the option. Whereas if the option is subpar, then the termination condition is going to be encouraged to shrink it. And then there's a third term over there, which tells us how to change the policy over options. And this is actually just saying you should take better options more often, okay? There's one little bit at the front, which is this beta theta term. This is essentially something that you can think of as a sort of off-policy termination correction. So basically, you can only tell an option, the policy over options what to pick when an option has actually terminated. And so this is why the beta, if the beta is 0, that means you're continuing. This gradient term is going to do nothing. It's only going to play a role when the options actually terminate. And so this is an expectation. Of course, the way that we usually solve these problems is not by computing the expectation, but actually taking samples and doing stochastic gradient descent. And so this is sort of the essence of the algorithm. I'm going to also point out that here I'm assuming that you want to do a policy gradient over all of these components. Of course, in some cases, you may want to do something else for the policy over options. And so it turns out that there's a lot of interesting special cases for writing out this formula. So the experiments that we've been doing with Option Critic are on top of deep neural networks. This is the usual sort of Atari framework where we have layers of convolutions, and then typically we have at the output these quantities that describe policies, termination conditions, value functions over options, and so on. We can do training using DQN or using the A to C framework, so the advantage after critic framework, which we call in this case A to OC, because we have options, not actions. And the only thing that you need to tell the system is how many options it should be looking for. And other than that, everything else is learned sort of on. And so these are results that were published last year in AAAI. Here we looked at several Atari games. The red lines are the benchmarked results from the Nature paper from DeepMind. The green curve is Option Critic learning. The amount of experience on the x-axis is what the systems reported in the Nature paper were given. And so Option Critic gets the same amount of experience in this case. And the interesting thing here is that the learning within a single task is actually competitive to solving the task using the usual DQN framework. Sometimes actually Option Critic does much better with this amount of experience. Sometimes it does a slightly bit worse. But this has been, at least to me, the first time that we demonstrated that one can learn the temporal abstractions as well as the policies that chooses them at the same time and not get slowed down and bogged down by the fact that now we have to learn more things. And I think, part of this certainly is the fact that we have one neural net that shares representation, and so some of the knowledge is shared between these pieces. That gives us an advantage. Out of 8 games that we tested now, we do better than the published results in 7. I have to say the A3C version tends to be superior to the DQN version, at least according to our findings, and both of these are available as code actually on our data. We also looked at transfer learning, of course, because we wanted to see if the options would actually be beneficial for transfer. And so here, this is the usual forums task, where you learn how to navigate to a specific goal state, and once you're done with that, the goal jumps somewhere else at random, and so now you have to relearn. And so what you see in the picture is the red and yellow are after critic and SARSA with just primitive actions. So you can see that once the goal has changed, they actually have quite a bit of trouble adapting to that. They'll need a lot of experience. And then we're looking at option critic with 2 options in green, and the other curves that are at the bottom are 4, 6, and 8 options. And in this particular case, the more options you have, actually, the better off you are in terms of the speed of learning. Now, an interesting point is that the objective that I gave you is not a regularized objective, right? You're just trying to optimize for the task. But you could be doing regularization, and this might help you in a variety of ways. So one way that regularization has been found to help in policy gradient is by doing some form of entropy regularization in order to encourage exploration, and in our case we would also like to encourage diversification of these options. So that's definitely useful. But there's a phenomenon that's specific to the options framework that requires extra regularization. And so in order to understand this, consider what's the best thing to do when you have a single task. Well, we know from Bellman that there is an optimal policy that uses just primitive actions. And so if all you're trying to do is optimize returns, the best thing for the agent to do is to maybe bootstrap itself with using some temporal abstraction, but then essentially just dissolve that temporal abstraction into one gigantic policy that just takes primitive actions. And so we wanted to prevent this effect because we do have this feeling that the abstractions might be useful at some later time. Certainly in the transfer learning setting they would be useful. And so the sort of intuition that we started using is that we would like the agent to be penalized for choosing among the options more so than for choosing among primitive actions. And so there's, in psychology literature, there is this idea of a deliberation cost. If the agent has to sit there thinking, that is consuming energy, but also perhaps the agent is missing some opportunities to act. So if you're a predator, and you're sitting there thinking, the brain might just run by, and now you missed it. Okay, and so we're trying to capture this intuition. And in our case, of course, there's other sort of considerations at this point. For example, if the policy of our options were a planner, okay, then calling the planner certainly might be expensive because you're going to have to invoke a different style of process. So the idea of the deliberation cost is that every time that the agent has to choose among its options, it's going to incur cost. This cost may depend on the state and the option, or maybe it won't. Okay, so now there's lots of different choices that you can do this. You can make it proportional to the number of options that the agent has at its disposal. You can look at runtime, a variety of other things. The interesting point is that this deliberation cost is associated with a value function of its own. Okay, and so we can write down Bellman equations for deliberation costs, and there's going to be some value function QC that's associated with this. And so now we can essentially take a regularized objective that wants to maximize reward while also not deliberating too much. Okay, and so this is the optimization that we have on the board there. And of course, as usual, you're going to have a regularization constant that tells you what's the trade-off. So how much do you want to avoid deliberation? If we set it to 0, we only care about rewards. And the higher you make it, the less the agent is going to want to think about its option choices, and it'll sort of get committed to doing longer options. Interestingly, one can show that this formulation is actually equivalent to looking at the advantage of the current option and the other potential options compared to the baseline. And so you won't allow the agent to switch out of the current option unless there's an option that's at least some amount better. Okay? And so it becomes a restriction on the advantage function. So what's the effect of this kind of regularization? Here we have some training curves and also some termination rates in 4 of the Akari domains. Yellow doesn't have any of this deliberation cost regularization. The other curves have the regularization. Red has the most regularization, okay? So what you see on the left-hand side is that the yellow agent typically is slower to learn, not always, but typically. You also see, of course, that the yellow agent ends up terminating 100% of the time after one step, right? So it essentially takes the options, dissolves them to primitive actions, and then it's done. Whereas the other agents actually keep their temporal abstractions over time. So it's kind of what we would hope to see. Now this is a qualitative example of what happens. This is a game of Amidar. It's a little grid, you have to walk around. And so the rightmost picture there shows what happens with option critic. Each of the little segments, colored segments, is one option being executed in this case. And so you see a lot of fragmentation, right? That's because the options are all sort of being shortened and they become primitive actions. If we add this regularization for the deliberation clause, we actually get nice chunks where the agent is committed to doing a specific option. And then the picture that's closest to me actually shows where these options terminate. And interestingly, they seem to terminate at bottleneck states. Okay? They terminate at hallways and places where the agent actually has choices of where to go. So I don't yet know what to make of this, but I think it would be an interesting thing to think about, right? As Matt was pointing out, bottlenecks seem to have sort of a very strong meaning, and some of what they're falling out of this formulation as well. So just to conclude, I would like to say that Option Critic is a solution for using sort of policy gradient methods and this framework of continual construction of temporal abstractions. We really need to do more empirical work in option construction. We have code online. I know some of the people I've talked to have been using our code. So if you want to give us feedback on that, that would also be welcome. One of the places where not a lot of work has been happening lately is construction of option models. We've all been, very happy working on the value policy framework, but the option models actually are also very critical if you're going to actually be planning. And because of this sort of behavioral program interpretation, there's an interesting possibility of integration with neural Turing machine and other kinds of programs for sort of synthesizing programs using neural interpretations. So I will stop here, and I'm going to put out my challenge slide.
Well, first of all, let's thank the speaker for this amazing talk. Now, before having questions from the audience, we'll have this last challenge of the workshop. In your talk you talked about option critic framework, and you have been able to learn these temporal abstractions without extra cost, but there was the benefit of them was on the demonstrating let's say simpler tasks, but not that much in Atari games and more complex environments. So I think and I think it's the same in many of the architectures, fiddle networks and option critique. They claim meeting non-hierarchical baselines in several settings, but in fact they're not really applied to everywhere with the mainstream Temporal algorithms are applied. And so is it a clear advantage everywhere, or is there more work to be done there? Anecdotally, these wins in hierarchy also seem hard to reproduce. There's many groups that have been working reproducing, for example, fun architecture and have struggled. So the key questions for deep hierarchical reinforcement learning and hierarchical reinforcement learning in general is the current research in deep hierarchical, is it rigorous enough and reproducible enough? This is linked to some other very interesting work you have been doing in this area to justify the existing claims. And if not, what steps forward do we need to take in this direction?
Okay, so thank you for the challenge. It is indeed one of the subjects that's close to my heart, and I gave a talk earlier today about this issue of reproducibility in reinforcement learning. So it is, I think, perhaps slightly more difficult to reproduce results in hierarchical reinforcement learning in some cases. And that has to do perhaps with the amount of computation that we have at our disposal and the amount of resources that we have at our disposal. We've made it a point to make the code of Option Critic in these two versions available, and people seem to be able to be using the code successfully, and they have in fact reproduced our results according to sort of anecdotal evidence that I've been hearing at NIP, so that's all good. That makes me very happy. We will continue to do that. I think feudal networks have an extra layer of complexity that makes it hard to open source the code, and so as a result of that, perhaps that's a little bit harder to reproduce. But I think we have a lot of potential for doing this successfully because the domains are available, a lot of the code is available, a lot of the ideas are available. It's just a matter of sort of pouring in the resources into it. And so one of the things that I've actually said at the end of my other talk about reproducibility is I think those of us who are in a position to sort of have large amounts of computational infrastructure, it's good for us to find ways to make this available at low cost to academic environments and to people in the environments who just don't have access to this kind of thing. I think this is happening already to some extent. Many of the companies have a form of academic grant that grants access to CPUs. That would help us, I think, with the reproducibility more. I mean, the other thing that I will say is it's useful if more people actually try to apply these frameworks in different kinds of domains, and it's useful for us to receive feedback in terms of what kinds of things you guys try and what works and what doesn't, so that we can also think up, if things fail, you actually get good information, and that stimulates the research. So that's useful. So I'll stop there, and I'm happy to take any other questions.
Hello. Just a quick question. So for the in the option critic, when you add the switching costs for different options, have you considered something I don't know, more theoretical? For instance, you could imagine that one reason that you would want to have temporally extended options is for the benefit of exploration.
That's certainly a good point. And so, in fact, having long options will allow you, if you're using call and return execution, to kind of be persistent in terms of the exploration rather than, so if you're doing, let's say, epsilon greedy, right? Instead of being stuck in one small area, the option might take you to very different parts of state space. We have not done a regret-style analysis of this aspect. There was actually a really nice paper in the main conference by Renan Free and colleagues that looked at regret bounds, not for option critics specifically, but for options in general. And there is a term in his bound that actually, I think, has some equivalent to this notion of deliberation cost, but we haven't yet looked at the paper carefully enough to be able to say, but certainly that's good.
Thank you.
Hi. I have a question about the distribution of option selection. Have you visualized it during your tests? And also, do you have an intuition about what might be a good distribution to look for between the options selected?
So we use very simple things for the policy over options. So in the A2OC framework, it's essentially spawning multiple threads, and so each of them is actually on policy, and we do epsilon 3D exploration. So nothing fancy there. With DQN, we have a replay buffer. We haven't visualized, I don't think, the policy and what the policy does. Although we've looked in several instances at what the options themselves do. How to do exploration when you have options in general, like what's the best way to do exploration, I think is a pretty open research topic that hasn't really received that much attention.
Thank you. So, during the talk, you mentioned the phenomenon of length collapse between the length collapse in the options. So, is this phenomenon related in any way to the number of options that you have? Because maybe if the number of options is lesser than the number of actions, then it would probably be difficult for length collapse to happen because it's difficult to achieve optimality with a small number of with reduced action states.
So we looked at this, and actually the number of options doesn't really help you there, because intuitively, you can take one option, right, and turn it into an optimal policy, or you can take two of them. They're very free to do inside of each option to do many different things, right? We don't have specific subgoals that they have to restrict. I think if instead of specifying a number of options, you actually specified subgoals, then what you're saying would be true, but in our case it doesn't.
Thanks.
Okay, very good. I think it's time for the panel. So let's thank one more time our last speaker, Doina Prikop.